According to National Electrical Code Section 240.4b, overcurrent devices should not exceed 80% of the ampacity of the conductors they protect. In a scenario where conductors are sized for 1500 amps, the maximum allowable overcurrent protection is calculated by multiplying 1500 amps by 0.8, resulting in 1200 amps. Therefore, rounding up to 1600 amps for overcurrent protection is not permissible. Since rounding up the overcurrent protection is not allowed, increasing the conductor ampacity is not necessary. If the thermal-magnetic breaker meets the requirements for adjustable setting circuit breakers, such as being located in a suitable enclosure and accessible only to qualified personnel, it can be set for 1500 amps. However, it is crucial to ensure that the breaker is specifically listed for the application and that its adjustable setting range includes 1500 amps. In conclusion, a thermal magnetic breaker with a setting of 1500 amps should be used, ensuring it meets the requirements for adjustable setting circuit breakers. There is no need to increase the conductor ampacity. This explanation delves into the application of the National Electrical Code, specifically addressing the sizing and selection of overcurrent protection for a 1500 amp service entrance feeding multiple motors within a motor control center, or MCC. The primary concern revolves around whether it is permissible to utilize a PD frame size thermal magnetic circuit breaker and round up the overcurrent protection to 1600 amps, given that the MCC bus is also rated for 1600 amps. Furthermore, the question arises whether the conductor ampacity needs to be increased if such rounding is allowed and whether the breaker's adjustable setting feature can be employed to precisely match the 1500 amp requirement. The National Electrical Code Section 240.4b serves as the cornerstone for determining the appropriate overcurrent protection for conductors. This section stipulates that overcurrent protection devices, such as circuit breakers or fuses, must be selected and installed in a manner that does not exceed 80% of the conductor's ampacity. This rule is in place to prevent conductors from being subjected to currents beyond their safe operating limits, which could lead to overheating, insulation damage, and ultimately, electrical fires. Applying this principle to the scenario at hand, where the conductors are sized for 1500 amps, the maximum allowable overcurrent protection is calculated by multiplying 1500 amps by 0.8. This calculation yields a result of 1200 amps. Therefore, according to the National Electrical Code, it is not permissible to round up the overcurrent protection to 1600 amps, even though the MCC bus is rated for that capacity. The primary reason for this restriction is to safeguard the conductors, ensuring they are adequately protected against overcurrent conditions. Since the overcurrent protection cannot be rounded up to 1600 amps, there is no requirement to increase the conductor ampacity. The conductors are already sized to carry 1500 amps, which is sufficient for the intended load, provided that the overcurrent protection is set at or below 1200 amps. Attempting to increase the conductor ampacity without a valid reason would not only be unnecessary, but also potentially lead to increased cost and complexity in the installation. Thermal magnetic circuit breakers, like the Siemens SPD type, offer adjustable settings which can be advantageous in certain applications. However, the use of adjustable setting circuit breakers is subject to specific requirements outlined in the National Electrical Code. These requirements typically include that the circuit breaker must be located in a suitable enclosure, accessible only to qualified personnel, and listed for the specific application. If the thermal magnetic breaker meets all the necessary requirements for adjustable setting circuit breakers, it can be set for 1500 amps, provided that the breaker's adjustable setting range includes this value. This would allow the overcurrent protection to be precisely matched to the conductor ampacity, maximizing the system's efficiency and performance. However, it is imperative to verify that the breaker is indeed listed for the specific application and that its adjustable setting range encompasses 1500 amps. Failure to comply with these requirements could result in code violations and potentially compromise the safety of the electrical system. In summary, The appropriate course of action is to utilize a thermal magnetic circuit breaker with a setting of 1500 amps, ensuring that it meets all the requirements for adjustable setting circuit breakers as stipulated by the National Electrical Code. There is no need to increase the conductor ampacity, as it is already adequately sized for the intended load. By adhering to these guidelines, the electrical system can be safely and effectively protected against overcurrent conditions, while also optimizing its performance and efficiency. To further elaborate on the topic of circuit breaker sizing and application, it is essential to consider various factors that can influence the selection and setting of overcurrent protection devices. These factors include the type of load being served, the characteristics of the electrical system, and the applicable codes and standards. Different types of loads such as motors, transformers, and lighting circuits have varying current characteristics. Motors, for example, typically draw high inrush current during startup, which can be several times their normal operating current. Transformers, on the other hand, may experience inrush currents when initially energized. Lighting circuits, depending on the type of lighting, may also exhibit unique current characteristics. The overcurrent protection device must be selected and set to accommodate these varying current characteristics while still providing adequate protection against overcurrent conditions. The characteristics of the electrical system, such as the voltage, available fault current, and grounding configuration, can also influence the selection and setting of overcurrent protection devices. The voltage of the system determines the voltage rating of the circuit breaker, while the available fault current determines the interrupting rating of the circuit breaker. The grounding configuration of the system can affect the type of overcurrent protection required, such as ground fault protection. The applicable codes and standards, such as the National Electrical Code, provide detailed requirements for the selection, installation, and setting of overcurrent protection devices. These codes and standards are designed to ensure the safety and reliability of electrical systems and must be strictly adhered to. When selecting and setting a circuit breaker, it is crucial to consult the manufacturer's specifications and instructions. The manufacturer's data provides valuable information about the circuit breaker's characteristics, capabilities, and limitations. This information is essential for ensuring that the circuit breaker is properly applied and will function as intended. In addition to the factors mentioned above, it is also important to consider the coordination of overcurrent protection devices. Coordination refers to the selective tripping of overcurrent protection devices such that only the device closest to the fault will trip, while upstream devices remain unaffected. Proper coordination minimizes the extent of the outage and allows the rest of the electrical system to continue operating. Coordination studies are typically performed to determine the appropriate settings for overcurrent protection devices to achieve selective tripping. These studies involve analyzing the time current characteristics of the various overcurrent protection devices in the system and selecting settings that provide adequate protection while also ensuring coordination. In the context of a motor control center, or MCC, the overcurrent protection of individual motor circuits is particularly important. Motor circuits typically require both overload protection and short circuit protection. Overload protection is designed to protect the motor from excessive current draw due to mechanical overload or other abnormal operating conditions. Short circuit protection is designed to protect the motor and the electrical system from high magnitude fault currents resulting from short circuits. Motor overload protection is typically provided by thermal overload relays, which are designed to trip when the motor current exceeds a predetermined value for a specified period. Short circuit protection is typically provided by fuses or circuit breakers. The selection and setting of motor overload relays and short circuit protection devices must be carefully coordinated to ensure that the motor is adequately protected without causing nuisance tripping. In addition to individual motor circuits, the MCC itself must also be protected against overcurrent conditions. This is typically accomplished by providing a main circuit breaker or fuse at the incoming power supply to the MCC. The main overcurrent protection device must be sized to protect the MCC bus and all the individual motor circuits within the MCC. The selection and setting of the main overcurrent protection device must be coordinated with the overcurrent protection devices of the individual motor circuits to ensure selective tripping. Furthermore, it is essential to consider the ambient temperature when selecting and setting overcurrent protection devices. The ampacity of conductors and the trip characteristics of circuit breakers can be affected by ambient temperature. Conductors have a lower ampacity at higher ambient temperatures, while circuit breakers may trip at lower current levels at higher ambient temperatures. Therefore, it is necessary to apply correction factors to conductor ampacities and circuit breaker trip settings to account for ambient temperature effects. These correction factors are typically provided in the National Electrical Code and the manufacturer's specifications. In summary, the selection and setting of overcurrent protection devices is a complex process that requires careful consideration of various factors, including the type of load being served, the characteristics of the electrical system, the applicable codes and standards, the manufacturer's specifications, the coordination of overcurrent protection devices, and the ambient temperature. By properly addressing these factors, it is possible to ensure that electrical systems are safely and effectively protected against overcurrent conditions.